In this video, we will be working on solving logarithmic equations. Now, getting started, we have two separate examples, two different log equations that take different forms. Now, the first log equation, all of the terms in the equation are logarithms. We have three different logarithms in there. In the second equation, we have two logarithms, and the third term in the equation is not a logarithm, but is a constant term, a number. So the way that we approach solving logarithmic equations depends on whether or not the equation is all logarithms or whether there is also a constant term in that equation. Now, if there's a constant term, it doesn't have to be already isolated in that equation. For example, I could have rewritten this equation as log base 3 of x plus 6 minus 2 is equal to log base 3 of x minus 2. Now, these are the exact same equations. I just moved things around, but notice that this equation still does have that constant term in it. So we're going to get started looking at the first type of equation. So notice that examples 1, 2, 3, and 4, every single term in the equation is a logarithm. Same thing happening in example 5. Every term has a logarithm. On the second page, we're going to look at a few examples where we definitely do have some constant terms showing up in those equations. So to solve equations of the first type, where every term in the equation is a logarithm, we use the logarithmic one-to-one property, which is this property right here. And this property says that if you have two logarithms that are equal, and the two logarithms have different expressions on the inside of the logs, then those different expressions must actually be the same thing. So I want to be very clear here. We're not coming in and dividing both sides of this equation by log base b to cancel these out, because that does not make sense to divide by log base b. Log is a function, but instead we are actually applying this property. So let's see that in action in example 1. Example 1, we have log base 2 of 5x minus 1 is equal to log base 2 of 2x plus 17. The logarithmic one-to-one property says that because our logarithms have the same base, it must be the case that 5x minus 1 is equal to 2x plus 17. So now we have simplified this equation from a logarithmic equation to a simple linear equation that we can now solve. I'm going to subtract 2x from both sides, leaving me with 3x minus 1 is equal to 17. I'll then add 1 to both sides to get that 3x is equal to 18, and divide both sides by 3 to get that x is maybe equal to 6. And I say maybe equal to 6 because we have to make sure that our potential solution does not violate the domain of these logarithmic functions. So remember, in a previous lesson, we learned that the input to a logarithmic function must be greater than 0. So now we have to check our solution. When x is equal to 6, the inside of our first logarithm is 5x minus 1, so I'm substituting in 6. 5 times 6 minus 1 is 29, which is greater than 0. So that does not violate the domain of that first logarithmic function. I'm now going to plug 6 into the other logarithm. 2 times 6 plus 17 is also greater than 0. So this does not violate the domain of the second logarithmic function. And so x equal to 6 is a valid solution for that equation. Moving on to example 2, both of these logarithms have a base of 10. The base is not written, but we know that when we see log with no base, it is understood to be the common log base 10. The logarithmic one-to-one property says that because the bases of these logarithms are the same and the logs are equal to each other, then the insides of the logarithms must also be equal to each other. So I set x minus 7 equal to 5 minus x. Again, I'm not dividing by the log. I am simply applying the property that is boxed in orange above. I'm going to go ahead with solving this equation. I'll start by adding x to both sides, giving me 2x minus 7 is equal to 5. I'll then add 7 to both sides to get that 2x is equal to 12, and I'll divide both sides by 2 to get that x is equal to 6. And now we are going to check if this solution works. I'll start by plugging 6 into the inside of the first logarithm, which is x minus 7. 6 minus 7 is equal to negative 1, which is not greater than 0. So the solution of 6 violates the domain of that first logarithm, and so this can in fact not be a solution. So example 2 has no solution. If we substitute in our x value and we get an expression on the inside of the logarithm that is negative, that is less than 0, then we are not allowed to use that solution, because as we know, the input to a logarithmic function must be greater than 0. Here we are in example 3. Again, we have only logarithms in the equation, but the difference between examples 1 and 2 and example 3 is example 1 had a single logarithm equal to a single logarithm. So did example 2. There's only one log on this side, and there's only one log on the other side of the equation. Example 3 is different because there's two logarithms joined by a subtraction sign on the left side of the equation and only one logarithm on the right side. So what would be ideal is if we could figure out a way to get the left side of the equation to only have one logarithm in it. So it's very good that we have already covered properties of logarithms that tell us that if we are subtracting two logarithms, we can condense them down into a single logarithm by using the quotient rule for logarithms. Quotient rule tells us, I'll just remind us of that rule. It says log of m minus log of n is equal to log of m divided by n. So I can condense this down into a single log with an input of 3x minus 4 coming from the first logarithm. So this 3x minus 4 is coming from here. And in the denominator, I will put x plus 1. So I have simplified the entire left side of the equation. So I rewrote all of this entire difference. This entire difference we rewrote as this one single logarithm using the quotient rule. The right side of the equation I will leave alone because it already had just one single log. And now we have something that looks more like example 1 and example 2, where we only have a single log on the left side of the equation and a single log on the right side of the equation. So now we are ready to apply the logarithmic one-to-one property that says that the inside of that logarithm must be equal to the inside of the logarithm on the other side of the equation. So we are essentially now dropping the logarithms and setting the insides equal. To solve this equation, I'm going to multiply both sides by x plus 1 to get rid of the denominator on the left side of the equation, which leaves me with 3x minus 4 is equal to 2x plus 2. Make sure to distribute that 2. I'll subtract 2x from both sides and add 4 to both sides of the equation to give me that x is equal to 6. And we again need to go and check this solution. So when we look back at the original equation, we're looking for what are the inputs to the logarithms. Well, the inputs we had were 3x minus 4, x plus 1, and 2. We don't have to check the inside of the log that has 2 on the inside because it's always going to be 2 on the inside. We do need to check the ones that have an x on the inside. So replacing x with 6, 3 times 6 minus 4 is 18 minus 4, which is greater than 0, so that works. We're checking the x plus 1, replacing x with 6. 6 plus 1 is 7, which is greater than 0, so that does not violate its domain. And x equal to 6 is our solution. Moving on to example 4. Example 4 is kind of similar to example 3 in the sense that example 4 has two logarithms on the left side of the equation, but this time they are joined by an addition sign rather than by a minus sign. So So when the logarithms were joined by a minus sign, we used the quotient rule to combine them into a single logarithm. Properties of logarithms tell us that when we have logarithms joined by an addition sign, we should use the product rule to join them into a single logarithm. And the product rule says that log of m added to log of n is equal to log of m times n. So natural log of x plus 3 plus natural log of x combines into the single logarithm of natural log of x multiplied with x plus 3. I just chose to write the x in the front of the x plus 3. I will go ahead and distribute the x on the inside of these parentheses. This is natural log of x squared plus 3x is equal to natural log of 10. And now we have this where we're able to apply the logarithmic one-to-one property, because we have a single log on the left side of the equation and a single logarithm on the right side of the equation. So we can drop the logarithms and set the insides of the logs equal to each other. Again, we should not be seeing anything like, oh, we're dividing both sides by ln, because that is not what we are doing. We are simply applying the logarithmic one-to-one property. This is a quadratic equation. We haven't seen any quadratic equations so far yet in this video. So far, every time we have applied the logarithmic one-to-one property, we have been left with a linear equation, meaning that the highest exponent that showed up on x was 1. But now we have a quadratic equation. We solve quadratic equations by getting 0 on one side. So I'm going to subtract 10 from both sides of this equation to give me x squared plus 3x minus 10 is equal to 0. And we factor if we can. And we are able to factor in this case. Do notice that a is equal to 1. So I can go ahead and break this up into x and x. And I'm looking for two numbers that multiply to negative 10 and add up to positive 3. And those numbers are positive 5 and negative 2. Now we set both of our factors equal to 0 using the zero product property to get two potential solutions of negative 5 and positive 2. And again, I call them potential solutions because we have to go check that they do not violate the domain of the logarithmic functions that have x on their input. So we're going to check the negative 5 solution. I'll start by plugging it into the x plus 3. Negative 5 plus 3 is negative 2, which is not greater than 0. And so this solution will not work. I don't even have to check in the other solution. If it doesn't work for one of them, then it's not going to work for either one of them. Now let's check the potential solution of x is equal to 2. I'll plug that into the first logarithm, replacing x with 2. We have 2 plus 3, which is greater than 0, so that's valid. We also need to check it into the other logarithm that has x on the inside. Just replacing x with 2, 2 is greater than 0, and so x is equal to 2 is a valid solution. Moving on to our last example on this page, again, we have more than one logarithm on one side of the equation. On that right side of the equation, the logarithms are again joined by addition, which implies that we will use the product rule to combine those two logarithms into a single log. So we will have log base 3, and on the inside we will have 2 multiplied by 3x minus 4. On the left side of the equation, we do only have one logarithm, but it has this coefficient of 2 in front of it, and we haven't had any coefficients in front of our logs so far. And if you remember from the lecture on properties of logarithms tell us that we can use the power rule to send that coefficient of 2 to the exponent on the x, giving us log base 3 of x squared. To simplify this a little bit, I will go ahead and distribute the 2 that's on the inside of the log on the right side of the equation, giving us a 6x minus 8 as that input. And now we are ready to apply the logarithmic one-to-one property and set the insides of these logarithms equal to each other. We again have a quadratic equation, which we solve by getting 0 on one side. So I'm going to subtract 6x and add 8 to both sides of the equation. This quadratic equation can factor. I'm looking for two numbers that multiply to positive 8 and add up to negative 6. They are negative 4 and negative 2. Setting both of our factors equal to 0 give us two potential solutions of x is equal to 4 and x is equal to 2. And now we must go and check. So I am looking here back at the original equation at each of my logarithms that had an x on the inside. We don't have to check the one that only has a 2 on the inside. So starting with the potential solution of x is equal to 4, when I plug it into the first one, 4 is greater than 0, so that's perfectly fine. Plug it into the second one. 3 times 4 minus 4 is also greater than 0, so x equal to 4 is a valid solution. Let's check the second solution of 2. Plugging it into the first equation, 2 is greater than 0, so that is a valid solution for that piece. Going on to the next one, replacing x with 2, 3 times 2 minus 4 is also greater than 0, and so both of these values are solutions for this equation in example 5. Now we're on to the next page where we look at our second type of logarithmic equation, where we're no longer going to be able to apply the logarithmic one-to-one property because there's not going to be a log on the other side of the equation. There's instead just going to be a number, a constant number on the other side of the equation. And when that happens, what we do is we change the equation to an exponential form, which we learned how to do in a previous lesson. So looking at example 6, we have log base 5 of 3x plus 1 is equal to 2. We have just a number on the other side of the equation. We have log equal to a number. We're going to change this to an exponential equation. The base is 5. The exponent that goes on it is 2. That's coming from the number on the other side of the equation. And it's all equal to the input of the log. Remember, this is the definition of what a logarithm is. Simplifying here, we have 25 is equal to 3x plus 1. I'm going to subtract 1 from both sides, giving me 24 is equal to 3x. And then I will divide both sides by 3 to get that x is maybe equal to 8. And I say maybe because we still have to check that our domain is not being violated. I need to plug our potential solution of 8 into the inside of the logarithm and verify that that is greater than 0 before we can confirm that 8 is in fact a solution of this equation. Looking at example 7, yes, I do see that we have a number on the other side of the equation. Again, I would like to emphasize that the equation may not always be set up where there already is a number on one side of the equation. I mentioned this at the beginning of the video, but this equation also could have came in this form. It is your job to recognize that one of these terms is simply a number. And then you must use what we know about algebra and properties of logarithms to manipulate this equation until it looks like this. Until it looks like log of something is equal to just a number. So let's work on that. Well, for one, right now, we don't have a single logarithm on the left side of the equation. We have two logarithms that are joined by a minus sign, which tells us that we need to use the quotient rule to condense these two logarithms into a single log. So we have log base 3 using the quotient rule. We will divide those inputs of x plus 6 and x minus 2. And we still only have 2 on the right side of the equation. So now we do have log equals a number. And we're ready to switch to an exponential equation. The base is 3, the exponent that goes on it is 2, and it's all equal to x plus 6 divided by x minus 2. So we have 9 equals x plus 6 divided by x minus 2. We'll multiply both sides of this equation by x minus 2 to get rid of that denominator. Do make sure to distribute the 9 on the left side of the equation, giving us 9x minus 18 is equal to x plus 6. I'm going to subtract x from both sides of the equation to give us 8x. On the left side, I'll also add 18. So we have 8x is equal to 24. We'll divide both sides of the equation by 8 to get that maybe x is equal to 3. And then we have to go and check. So I'm going to take our potential solution of 3 and plug it into the insides of both of our logarithms to verify that they do not violate the domain and confirm that x is equal to 3 is a solution of this equation. Moving on to our last example, example 8. Again, we don't just have a single logarithm on the left side. We have two logarithms joined by a minus sign. So we will again start off with the quotient rule. If they were added, we would be using the product rule to combine these into a single logarithm. And now we are ready to switch to, this is the same example as example 7. Let's change this to a plus sign so we can see something different. So I changed this to a plus sign. Because this is a plus sign, now I'm going to combine these two using the product rule, which tells me that we will have a single logarithm, and the input to that will be the product of x plus 6 and x minus 2, which I will FOIL out and combine like terms to give me x squared plus 4x minus 12 is equal to 2. And now let's change this to an exponential equation. The base is 3, the exponent is 2, and it's all equal to x squared plus 4x minus 12. Go ahead and simplify that. 3 squared to give me 9. This is an exponential equation. We solve exponential equations by getting 0 on one side. Or rather, excuse me, this is a quadratic equation. We solve quadratic equations by getting 0 on one side. This can be factored. I'm looking for two numbers that multiply to negative 21 and add up to 4. Those numbers are positive 7 and negative 3. I'll set both of those factors equal to 0 to get positive 3 and negative 7 as two potential solutions. And I do mean potential because with log equations, you always have to go check. So I'm looking back at the inputs of those two logarithms. I'll start with the first potential solution of negative 7. When I substitute it in here for x, we have negative 7 plus 6, which is not greater than 0. So negative 7 cannot be a solution. Let's move on to check 3. 3 plus 6 is greater than 0, so it does work for that one. Let's check this one. 3 minus 2 is also greater than 0, and so it does work for the second one. So x equal to 3 is the only solution of that equation.